Okay, so we're going to talk a little bit about probability. So first we want to define a probability function. And the probability function, which we'll denote as P, is a mapping of a defined event onto a metric bounded by 0, meaning it cannot happen, and 1, meaning the event will happen with absolute certainty. And so when we think about what event are we talking about, think it could be any sort of political event, an election outcome, a coup, a war. And so we have sort of these events defined in a sample space, right, which we talked about previously in the set theory lecture. And so the probability function is a function, right? It's a mathematical equation. When I say function, I mean it's a mathematical equation. And we're just going to denote that by P because we don't know what that mathematical equation actually looks like. We're just going to say that one exists, and we don't know what it looks like. So we're going to denote it by P, and that's going to tell us whether or not the event can happen or whether it cannot happen, or somewhere in between, right? So in other words, it enables us to discuss the various degrees of probability of an occurrence in a systematic manner. The notation here you often see is the probability of, say, A, event A, or say an uppercase probability of event A, or say P, R, which means the probability of event A. Those are all common notations that you'll see in textbooks and online. So then let's define a sample space as S, which you should know what the sample space is from set theory. The probability of A equals the probability that outcome A will occur within the sample space S. And then we can define probability theory with three basic axioms or rules of probability. The first is for every outcome A, then the probability of event A is greater than or equal to 0. The probability of the sample space equals 1. Or the probability that we'll observe something with the sample space equals 1. And if A1, A2 to AN is a finite or infinite sequence of mutually exclusive events within the set of S, and you should know what mutually exclusive means from the set theory lecture, then the probability of the union of A1 and A2 and A3 all the way to AN is equal to the probability of A1 plus the probability of A2 plus the probability of A3 all the way to plus the probability of AN. In words, right, axiom 1 means that every event has a non-negative probability. Every event has a non-negative probability. 2 is the probability that some outcome within the sample space will occur is 1. Right? So some outcome in the sample space will occur is equal to 1. And the union of a finite or infinite sequence of disjoint mutually exclusive events have a probability equal to the sum of their probabilities. In practice, 3 is the axiom that we tend to use the most because it gives us some leverage on how to define some equations. We want to define what an independent event is. An independent event, if two events are independent, if the occurrence of one event provides no information about the occurrence of the other event. So if knowing who wins the 2016 presidential election tells us nothing about who wins the 2020 presidential election, then the events are independent. Of course, in that situation, there's probably a likelihood that those events are dependent. So maybe a better example would be if whether or not you eat dinner tonight is going to influence the 2016 presidential election, right? Probably no connection there. So formally, we would say events are independent if the probability of if the probability of the intersection of A and B equals the probability of A times the probability of B. So for example, if John draws a random card from a deck of 52 cards, right, then the probability that John draws a jack of clubs is 1 in 52, right? There's one of these cards in a deck of 52. So then if Mary draws a random card from a deck of 52 cards, the probability that she draws a jack of clubs is 1 in 52. Now, right, so in that case, right, so what we've done here is have John draw a card from 52 cards, restack the cards with all 52 cards, and let Mary draw from those same deck of 52 cards. And notice what Mary draws is independent from what John draws, as long as we've shuffled them up and everything, right? So then the probability that John and Mary both draw the jack of clubs is 1 in 52 times 1 in 52, and that equals something very, very much smaller than 0, right? Or 1, something very small. Okay, so then we want to talk about conditional probability. And conditional probability is important because most of our political relationships that we're interested in are conditional on one another, right? So what's the probability that a Republican votes for John McCain in the Senate election? What's the probability that China and the U.S. go to war given continued conflict in Taiwanese Strait? All these sort of things are conditional on, all these outcomes that we might be interested in as political scientists are conditional on other events. So going back to our card drawing example, what if Mary and John are drawing from the same deck of cards? Then the probability that Mary draws a jack of clubs is conditional on the card that John draws, right? In other words, knowledge of John's outcome provides us information about the probability that Mary draws a jack of clubs. So if John draws a jack of clubs from the deck, then we know that the probability that Mary will draw the same card is 0. But if John does not draw a jack of clubs, then we know that the probability that Mary will draw a jack of clubs is 1 in 51 instead of 1 in 52 since John has already drawn a card, right? So conditional probability we can set up as the probability of A given B, right? So this line means A given B. And that denotes the probability that A will occur given that event B has already occurred. So formally we can say the probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B, right? So we just have that defined here, the probability A given B. This is the conditional probability that event A will occur given that event B has already occurred. This part here. This part here in the numerator is the probability, the unconditional probability that event A and event B both occur. And the denominator here is the probability that, or the unconditional marginal probability that event B occurs. I say unconditional here because these things are not conditioned on anything else, right? So what's the probability of B, right? That's just the probability of B. It doesn't mean the probability of B given something else has already occurred. This right here statement is given the probability of A given that B has occurred, but these are unconditional probability statements. Okay, so here's an example. Imagine we have the following survey data for 100 individuals. We have whether or not they voted for Obama, they voted for someone else, and then this is just the total column. We have whether or not they're a Democrat, Republican, and this is the total column. So what is the probability of selecting a Democrat? Well, the probability of B, of selecting a Democrat, right? This is an unconditional probability. We're not saying what's the probability of selecting a Democrat given that they voted for Obama. We're not asking that. We just want to know what's the probability of selecting a Democrat. And that's just going to be 16 over 100. We have 100 total, and the probability of selecting a Democrat is going to be the total column here, 16. Right? So 16% chance we're going to select a Democrat. What is the probability of selecting a Democrat that supports Obama? So here we're asking for the intersection, right? Which Democrats support Obama? And that's going to be 12 out of the 100, right? 12 out of the 100, so 12%. So then what's the probability of selecting a Democrat out of this 100 given already selected an Obama supporter? So given that we've already selected someone that supports Obama, what's the probability that that person is going to be a Democrat, right? Well, we just go back to this equation and we plug in 0.12 here, 0.16 here. We do our division and we get 0.75, right? And that's conditional probability. Okay, so I talked a little bit, or in some of the notes I wrote up about randomness. And randomness just means that the outcome of some process is not deterministic. Right, so formally we can say the probability that event A occurs is between 0 and 1. We can call the outcome, or the thing that we want to study, a variable. In most sciences, the variable is an outcome of an experiment. So the outcome of an experiment is a random variable that takes on specific values with some level of probability. It doesn't mean it's chaotic. It doesn't mean it's unpredictable. It just means that it's non-deterministic. When we talk about the outcome of an experiment, what we really mean is the process that generated some outcome. This outcome is often represented by data as some dependent variable that we want to explain or we think depends on some other independent variables in our analysis. And so sometimes I'll refer to an experiment as a data generation process because I'm generating data, I'm generating outcomes with an experiment. The data generation process does not have to be a formal laboratory experiment. Instead, you might also, and lots of textbooks do, think about the data generation process as any process that generated the outcome of interest. So whatever process led to World War II, that's the data generation process. Whatever process led to the presidential election outcomes of the last 40 years in the United States, that's the data generation process. Those weren't experimental processes, but they led to some outcomes that we want to study as political scientists. Okay, so let's talk about random variables, which we'll get into, I think, a little bit more in the next chapter. Imagine a sample space S. We can define a random variable as a real valued function that is defined onto some sample space X. Again, we don't know what the function actually looks like. We just know that there's some mathematical equation there that helps us define this random variable. It is some function that assigns a real number to each possible outcome S within the set of X. There is no single random variable function, meaning I said we don't know what it is. There's no single random variable function. Instead, there's actually many different functions that can describe the outcomes of many different types of random variables. So I kind of lied when I said we don't know what it is. It's just that it's more so the case that there's so many different functions that each outcome that we want to study has its own function. Okay, so the mathematical function, for instance, that describes vote choice is going to be very different than the function that describes income. The possible outcomes for a single coin flip, if we go back to our sample space, our set theory lecture, our heads and tails, we can describe the outcome of a coin flip x as a function of a random variable, uppercase X. That is, some process X governs the outcome of a coin flip. For a single coin toss, this process is actually a Bernoulli probability mass function. So when I said we don't know what the functions are, this is a case of where we do know what that function looks like. For a coin flip, we know it's a Bernoulli probability mass function, which looks like this. We have the random variable x, and that event that we could observe is either going to be 1 if x equals heads and 0 if x equals tails. This random variable can be described with the probability mass function. The probability of x within the set of x is 1/2 or 0.5 if x equals 1 and 1/2 0.5 if x equals 0. Basically what the function is saying is that there's a 50-50 chance of landing heads and a 50-50 chance of landing tails, right? Which you probably already know. Suppose we flip a coin 2 times. The experiment can have 4 outcomes: heads, 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 tails, tails, heads, tails, tails. If x is a random variable where the number of times of heads is the outcome, then we have x equals heads, and that's 0 if it lands on tails, tails. It's 1 heads if it's heads, tails, or heads, tails, heads, and it's 2 heads if it's heads, heads, right? So here we can say the probability of x is heads is 0.25 if tails, tails, 0.50 for heads, tails, or tails, heads, and 0.25 if heads, heads, right? So a random variable is simply a variable that we can attach to a probability function to understand the probability of an outcome. Now, there's going to be lots of different probability functions based on different probability distributions. The distribution of a random variable is the collection of all possible outcomes along with their probabilities. This can be described by a table, a formula, or some sort of probability histogram. So a distribution, again, I think this is a really good definition once you know probability, but it's probably not so helpful if you don't understand probability yet. It is a collection of possible outcomes along with their probabilities. So if your outcome is who's going to win the 2000 presidential election, and it's between Hillary and Trump, right? Those are the outcomes. Those are the possible outcomes, and then we want to attach the probabilities, all the probabilities that we might observe, say a Trump victory, or all the probabilities that we observe Clinton victory, and that collection of probabilities is the distribution, right? That's the probability distribution. There are 2 types of random variables leading to 2 different types of distributions that we've talked about before in terms of measuring data. The first is discrete, and a discrete is a random variable that can only take on a finite limited number of different values. This would be categorical or ordinal variables. And there's continuous, right? A random variable that can take on a value at every interval within the sample space. And these are interval and ratio level variables. So a discrete variable would be the number of legs on a dog, right? So there'd be typically 4. Those are discrete. Continuous would be something like temperature or height. The type of random variable, discrete or continuous, determines the type of distribution function. A discrete random variable has a discrete distribution. If a random variable x has a discrete distribution, the probability function, or PF, also called the probability mass function, or PMF, is defined as a function such that for every real number x, function of x equals the probability of x equals the outcome or event x, right? Where the lowercase x is a hypothetical single value that can take on only discrete values. It is the event in the sample space from the random variable x, and x is that random variable, or you can think of it as the sample space, all the potential outcomes that we could observe. So the random variable x is the number of heads on a coin flip. The probability of x equals heads equals 1 minus p times x equals t, which would be if it lands on tails, right? So we know the probability that x lands on tails is 0.5, and so we also know that the probability of x lands on heads is 1 minus 0.5, so we just place this statement here with this 0.5 here, so we have 1 minus 0.5, and that tells us the probability of x equals heads is a 0.5. It's a pretty simple example. We can plot that with bar plot here, the distribution of the number of heads on 10 coin flips with a fair coin. So maybe we observe no heads, 1 heads, 2 heads, 3, 4 heads, 5 heads, 6 heads, 7 heads, 8 heads, 9 heads, 10 heads, right? So the chance that the probability that lands on heads 10 times, right, if we flip the coin 10 times is really low. It's less than 0. And the fact that it doesn't land on tens, also really low, right? It's approaching 0. It's most likely that it's going to land on heads 50% of the time, right? So we see the largest sort of bar here at 5 heads. And so if we did the calculations, we could see that it's going to land on heads 5 times. There's a 25% chance that we observe this outcome. There's a 25% chance that we observe it land on heads 5 times. There's about a 20% chance that it lands on heads 4 times, and 20% chance that it lands on heads 6 times. So this is what a probability mass function or probability function does, right? I say it's the collection, when I say that the distribution is the collection of outcomes with their assigned probabilities, this is the collection of outcomes, observing 2 heads, 3 heads, 4 heads, 5 heads, 6 heads, with their probabilities. So the probability we observe 4 heads is a little more than 0.2. The probability we observe 5 heads is 0.25, right? And so this is the probability distribution here.